So we will end the discussion of linear regression with one variable with discussing the idea of the sampling distribution of the OLS estimator. As we have stated before, when we take a sample from a population and we try to estimate some parameter for the population. So suppose we are trying to estimate the population mean, and suppose we are trying to estimate the population mean, and then we estimate using the sample mean. We take a random sample and we calculate the sample mean, and we use it as an estimate for the population mean. Now had we taken a different sample, we would have got a different value of the sample mean, and hence the sample mean itself could vary from sample to sample, right? So the value of the sample mean would vary from sample to sample. So there is an underlying uncertainty associated with the sample mean, which will depend upon which particular entities are included in a particular sample. So hence the sample mean follows a particular distribution, and that distribution is known as the sampling distribution of the mean. So similarly, when we look at a regression done where we are trying to understand some population relationship using data from a particular sample. Now what are the two parameters that we are estimating? We are estimating the population parameters beta 0 by beta 0 and beta 1. These are the population parameters that we want to estimate. We are estimating it using a sample, and we are getting values of beta 0 hat and beta 1 hat from a particular sample. Now had we taken a different sample, we might get a different value of beta 0 hat and a different value of beta 1 hat. Hence these values beta 0 hat and beta 1 hat themselves are can be thought to be as random variables, and they follow a certain distribution, and this distribution is known as the sampling distribution of the OLS estimator. So whenever we estimate beta 0 hat and beta 1 hat, we have to be careful to or we have to be aware of the idea that had we taken a different sample, we might have got different values of beta 0 hat and beta 1 hat. So how sure are we that the values of beta 0 hat and beta 1 hat we have got are, how sure are we about the variance, or about how can we say something about beta 0 hat and beta 1 hat? So here we arrive at the idea of the sampling distribution and the idea that there is a certain variance associated with beta 0 hat and beta 1 hat. So the OLS estimator is computed from a sample of data. A different sample yields a different value of beta 1 hat, also beta 0 hat. So this is a source of the sampling uncertainty of beta 1 hat. We want to quantify the sampling uncertainty associated with beta 1 hat, and using this sampling uncertainty we want to further test hypotheses such as beta 1 equals to 0. Why do we want to test this hypothesis? Basically the null hypothesis is that there is no correlation between y and x. Okay, there is no correlation between y and x. This is our null hypothesis. If there is no correlation between our y and x, then beta 1 will be equal to 0. This is the null hypothesis that we want to test, and if we want to test this null hypothesis, then we will have to understand what is the uncertainty or what is the standard deviation associated with in the sampling distribution of beta 1 hat. All these things require figuring out the sampling distribution of the OLS estimator. So two steps are needed to get there. First, we have to understand what is the probability framework for linear regression and what is the distribution of the OLS estimator. So what is the probability framework? First, we have to understand all the probability facts associated with linear regression. So what is the population? The population is the entire population within which you are trying to find out some relationship between y and x. In this particular case, where we are looking at the relationship between test score, which is your y, and student teacher ratio, which is your x, then our population of interest are all possible school districts. But we do not have data for all possible school districts. We have data for a subset of school districts, which is 420 school districts. That is our sample that we have. So the random variables here we are interested in is y and x, which is test score is y and x is STR. And because there are two variables that we are looking at, we are interested in the joint distribution of y and x. So we assume that the population regression function is linear. The first least square assumption states that the expected value of u given x, or the expected value of the error that you will make once you have fit the regression line, the expected mean should be 0. X and y have non-zero finite fourth moments, which is the third least square assumption, and the data will be collected by simple random sampling, which implies that xi and yi are chosen randomly, and hence they are independently and identically distributed. Right. So so what is the sampling distribution of beta 1 hat? We are trying to find out what is the sampling distribution. So when you try to find out, you are basically interested in the mean and the variance. Of course, you might be interested in other things such as skewness and kurtosis also, but right now we are not worried about skewness and kurtosis. We are mainly interested in the mean and the variance of beta 1 hat. So because the variance of beta 1 hat, if we take a large n, when we take a small n, we don't quite know what the sampling distribution is. But when n is large, then by law of large numbers, the variance of beta 1, the expected value of beta 1 hat will tend towards the true population parameter. That is, the expected value of beta 1 hat, remember, is a mean beta 1 hat, right? So the mean of beta 1 hat will tend towards the true population parameter in probability, when this is by the law of large numbers. And further, by the central limit theorem, when n is large, the sampling distribution of beta 1 hat will be well approximated by a normal distribution. So if you will recall the central limit theorem, if each of the entities I equals to 1 to n, they are IID, and expected value of v is equal to 0, and variance of v is sigma square, which is bounded, it is not infinite, then when n is large, this is approximately distributed according to a standard normal distribution with mean 0. As we said, the mean is 0 and the variance is given by sigma square nu by n, or this is the standard error of the particular variable that you are looking at, which in this case is v. So deriving, so this is the sampling distribution. The expected value of beta 1 hat is beta 1. So OLS is unbiased. This is a good thing. So we want to find that value of beta 1 hat, which when the sample is large, gets closer and closer to the true population beta 1. We want to understand what the true correlation or the true relationship between y and x is, and when n is large, whatever beta 1 hat we get, the expected value of beta 1 hat gets closer and closer to the true population beta 1. What is the variance of beta 1 hat? Now we can derive a formula, we can calculate the standard error of beta 1 hat. In small samples it is complicated, in large samples beta 1 hat is normally distributed by the central limit theorem. Now the variance of beta 1 hat is given by this somewhat complicated formula, which is 1 by n multiplied by variance of xi minus mu x multiplied by ui divided by sigma x to the power of 4. So basically what the numerator is the how far the each of the x's are from the average x multiplied by each of the errors associated with this. So how this formula is derived is sort of complicated and is beyond the scope of this introductory course on regression. We will just take that this is what it is, and this is calculated by this variance of beta 1 hat is calculated by most softwares, by most regression softwares such as R. Okay. The idea is that you understand the fact that there is in fact a variance associated with beta 1 hat. Now if this variance of beta 1 hat is large, that means you will have less confidence in that particular beta 1 hat that you have got. It could take a range of values if the beta 1 hat is large. So when you calculate a particular z score, or your software will calculate a particular z score, where it will take beta 1 hat minus the expected value of beta 1 hat in the numerator divided by the root of variance of beta, or the standard deviation of beta 1 hat, and this will be distributed according to a standard normal distribution. So n with a mean 0 and standard deviation of 1. Once we have established this, we can now conduct hypothesis testing. Okay, so basically a lot of times when we conduct we do perform a regression analysis, we are many times interested in testing the hypothesis that in fact there is no correlation, or there is no relationship between y and n. And how do we test this hypothesis? We can test this hypothesis because beta 1 hat in large samples it tends towards the true population beta 1, and also this particular z score is distributed according to a standard normal distribution. Finally, this is how we this is the large sample distribution of beta 0 hat and beta 1 hat. So if interestingly we have to remember that we made certain assumptions for the OLS. What were the assumptions? The first assumption is that expected value of u given x is equal to 0. The second assumption is that of IID. Okay, all the entities are chosen independent, they are independently and identically distributed, and the third assumption is the variance of yi and variance of xi is bounded. So that is it is, it doesn't have fat tails. There are no large outliers in your regression. If these assumptions are met, then we can say by the central limit theorem and by the law of large numbers, we can say that the beta 1 hat will be distributed such that beta 1 hat will tend towards the true population beta, and also the summation, the sigma of that will be described by this particular sigma square of, or the variance of beta 1 hat will be given by this particular formula. Similarly, you can also derive the formulas for the variance of beta 0 which will be given by this. Okay, so the idea is that you have to understand that there is in fact such a formula associated with the variance of beta 1 hat and beta 0 hat. So this is where we will stop our discussion of the initial discussion of linear regression with one variable. In the next lecture, we will talk about hypothesis testing and confidence intervals for beta 1 and beta 0.